Now we'll tie in the matrix exponential to solving systems of differential equations. Suppose our system is x prime equals ax. I'm going to propose a form of solution. X is equal to e to the at times c, where e to the at is the matrix exponential, and c is a column vector of constants. If x is that, then x prime is its derivative, c being constants. All we need to consider is the derivative of e to the at. For that, we're going to use the expansion of e to the at. The derivative of I, since I has all constants, is equal to 0. A is a matrix that has all constants, and so the derivative of a times t is simply going to be a. When we get to the a squared t squared over 2 factorial term, we're just differentiating the t squared, and so we end up with a squared times t because the 2 divides out. Differentiating t cubed multiplies by 3. We have 1/2 a cubed t squared. The next term I'm sure you can guess would be 1 over 3 factorial a to the 4th t cubed, and so on. Well, folks, every term has a factor of a in it, and if we factor that out, we end up with a times the quantity of I plus at plus 1/2 a squared t squared plus 1 over 3 factorial a cubed t cubed, and so on. Well, that's a e to the at. Yeah, the chain rule works exactly in the same way for the matrix exponential as it does for exponential functions. Since e to the at is equal to a e to the at, when we had x is equal to e to the at times c, we end up with x prime is equal to a e to the at times c. But that gives us x prime is equal to ax, the exact system that we were just considering. So for x prime equals ax, with a containing constant entries, x equals e to the at times c is a solution. We're going to use that fact to solve the system of differential equations. X prime equals 0, 1, 1, 0 times x. In this case, a is 0, 1, 1, 0, but we already know what e to the at is. We saw it in a previous video. E to the at has entries hyperbolic cosine of t, hyperbolic sine of t, hyperbolic sine of t, hyperbolic cosine of t. So x is equal to that matrix, which I don't really want to read again, times c. All the work was done in finding the matrix exponential, but there's our solution. We can handle initial value problems and non-homogeneous systems using the matrix exponential and the formula that we found when we saw a variation of parameters. E to the at is phi. It's the fundamental matrix. So x equals e to the at times c plus e to the at times the definite integral from t naught to t of e to the negative as times f of s ds. Remember that e to the negative as is the inverse of e to the as. So that's why it appears with the e to the negative as in our formula. In our work, we're going to take t naught to equal 0, and I'll also remind you that the s in this context is a dummy variable. So we have a system here. X prime equals 1, 0, 0, 2x plus 3, negative 1. A is equal to then 1, 0, 0, 2. This is kind of nice. It's called the diagonal matrix, and it has a nice property that when we multiply it by itself, what ends up happening is we multiply the diagonal entries by themselves. So a squared is 1, 0, 0, 2 squared. A cubed is 1, 0, 0, 2 cubed, and so on. Putting this into the form of the matrix exponential, we have this is I plus a times t plus 1/2 a squared t squared, and so on. But we have a squared and a cubed in front of us. So in this case, e to the at is going to be 1, 0, 0, 1 for the identity matrix, plus t, 0, 0, 2t for a times t, plus 1/2 t squared, 0, 0. I'm not going to reduce over here. I'm just going to write it down as 2 squared t squared over 2. And then move on to the next. 1/3 t cubed, 0, 0. 2 cubed t cubed over 3 factorial, and so on. So e to the at has as its upper left entry 1 plus t plus 1/2 t squared plus 1 over 3. I wrote that as 1 over 3. It should be 3 factorial. T cubed, and so on. 0 for the upper right, 0 for the lower left, and then 1 plus 2t plus 2 squared t squared over 2 plus 2 cubed t cubed over 3 factorial, and so on. You might recognize these as actual exponentials. This boils down to e to the at is e to the t, 0, 0, and e to the 2t. That means that the complementary solution x sub c is e to the t, 0, 0, e to the 2t times c. Now, according to the formula that we saw above at the beginning of this video, x sub p, the particular solution, is, well, I was going to write phi. It's e to the at times the integral from t naught to t of e to the negative as times f of s ds. E to the negative as is simply e to the negative s, 0, 0, e to the negative 2s. We're just replacing t using negative s. So e to the negative as times f is that matrix times the column matrix 3, negative 1. That gives us the column vector column matrix 3e to the negative s, negative e to the negative 2s. That's what we're going to integrate. So we have e to the at times the integral from t naught to t of 3e to the negative s, negative e to the negative 2s with respect to s. That gives us e to the at times the column vector negative 3e to the negative s and 1/2 e to the negative 2s, and that's evaluated from t naught to t. For our work, we're going to say t naught is equal to 0 every time this pops up, unless you have an actual initial condition. So we have e to the at times negative 3e to the negative t plus 3, and that plus 3 comes from subtracting evaluating at the lower limit. T naught equals 0 gives us a 0 exponent. Then for the bottom entry evaluated at t and t naught equals 0, we have 1/2 e to the negative 2s minus 1/2. Well, e to the at was e to the t, 0, 0, e to the 2t. And I'm writing all this down because I want to show you something in particular that's going to happen in this case. Multiplying the fundamental matrix e to the at times what we just found is going to boil down to multiplying e to the t by the top entry and then 0 by the bottom entry, so it doesn't really contribute at all. And then 0 by the top entry and e to the 2t by the bottom entry. The result is negative 3 plus 3e to the t and 1/2 minus 1/2 e to the 2t, which I'm going to write down as negative 3 1/2 plus 3e to the t negative 1/2 e to the 2t. X was equal to e to the at times c, so e to the t 0, 0, e to the 2t times c plus xp, which is that negative 3 1/2 plus 3e to the t 1 half e to the 2t. That vector of constants, I'm going to rewrite using C1 and C2. And when we multiply that out, we end up with C1 E1 e to the t, as our top entry, and C2 e to the 2t as our bottom entry. You may notice looking across the first entry of all of our vectors that we have a C1 e to the t and a 3 e to the t. Likewise, in the bottom entry of our vectors, we have a C2 e to the 2t and a 1 half e to the 2t. We're going to combine those and let constants subsume the like terms. So I'm going to relabel our constants C3 e to the t and C4 e to the 2t. Add to that our x sub p, 3 1 half. And that's our solution. We've eliminated the redundancies by letting the constants absorb the 3 and the 1 half.